Hello, everyone, and welcome to the Interrupt Handler and PCI Diag utility. Thanks for joining. We will start now. My name is Daniel. I'm the presenter today. This is my email, danielb.django.com. Feel free to send me emails, questions regarding everything we are going to talk about. Let's start. So this is one of 4 webinars series that we host in this time of the year. Last week, we hosted an introduction webinar. We have an introduction webinar already on our YouTube and website. If you're not familiar with WinDriver, I recommend going to watch it. It gives a general information regarding WinDriver, how it works, what features we have. And this specific webinar will talk about the interrupt handler feature and the PCI Diag utility. This webinar will also be uploaded to our YouTube channel. So if you want to go back to it from tomorrow, I guess, you can go to our YouTube channel and watch it. Next week, we will host a direct memory access 101 webinar. This is, if you are not familiar with DMA, this is the webinar you should join. We also talk about more advanced features of DMA. We discuss the research we conducted comparing DMA types and DMA methods. But this happens also next week. This is part of the series. You can register on our website. Go to Media, News and Events, and you can see it. Last week, we launched WinDriver 16.3. This version includes mostly fixes. It has some enhancements. We will present everything on this webinar. It's on September. The reason is the summer break a lot of countries have. So you can download WinDriver 16.3, try it yourself, and join the webinar in the 19th of September. And we will talk about this version features and a multi-process driver. Okay, we have a special API for multi-process driver. I will talk about it today when I will talk about the shared interrupt between processes. So sign up for this as well, because we are going to elaborate much more on how to create a multi-process driver. We have more content. We have blog posts on our website under the blog section. You can see a comparative DMA research article, blog posts about interrupt types, how to access hardware with Python apps, a comprehensive guide for INFs. We have a video section on our website, which is also new. We have a demo that was recorded on the Embedded World exhibition in Germany on April. We have the previous webinars recording just there. And we have also an academy of WinDrivers Academy that includes more technical best practices videos on a variety of subjects, DMA, quick starts, how to distribute your driver, what is INF, how to utilize WDREG utility. So this is also happening on our website. You're welcome to enter the website and keep checking it, because we keep uploading more and more content, more technical content, and helpful. So what are we going to do today? We are going to have a quick, brief WinDriver overview, because we're not here for that. Then we're going to review the PCI Diag utility. Where can you find it? What can you do with it? We'll talk a lot about the interrupt handler okay, both the PCI Diag, but also our API and what is an interrupt and what the types of interrupt. We will talk about the sequence. We will have a live demo. Stay for it. It's cool and important. The types of interrupt and interrupt handler in the kernel plugin. We will also talk about transfer commands. What are transfer commands? How can you utilize them? How WinDriver can help you with creating transfer commands with ease. And we will also talk about the IPC, the inter-process communication. This is what we said earlier about the shared processes, okay? The multi-processes driver. We will have a quick overview and we will see how we can implement a shared interrupt on our driver. So let's have an overview of WinDriver. WinDriver is a driver development toolkit. Okay, it's a toolkit that gives you an API to communicate with your hardware. The thing is that it is much easier to create drivers with WinDriver than doing it alone. It is easier to develop and it is easier to debug. Okay, so WinDriver is a cross-platform, which means we work on Windows, Linux, and Mac OS. You define the parameters of your driver in a convenient GUI, friendly GUI application, and you get a code, generated code, not just the code, also INF if you work on Windows, but you will get a code that is generated automatically that you can build into an executable app, which is your driver. Okay, we will see it. We will not generate a code, but we will see the code of the PCI Diag and how can we modify it. We support any USB or PCI device, regardless of the manufacturer. And we developed samples for specific chipsets from Altera, Xilinx, and Lattice. This is not a plug-and-play solution because the samples were developed for specific devices, not all the devices by these manufacturers, but these are good start. So if you develop a driver for Altera, Xilinx, or Lattice manufacturers, we have samples that you can get inspired from, okay, and see how we implemented or developed a driver for these manufacturers. Very generally, the mechanism, okay, we have the user mode, the application layer. This is where our driver is taking place, and we have our API, WinDriver API, high-level API. I will talk about high and low-level APIs in the next slide. Our API, you can call high-level functions, and they communicate with low-level functions on the kernel mode. Okay, so you don't have to develop in the kernel, and you don't have to debug in the kernel. It makes the whole development process much easier with less crashes and hangs, because if you mess things up, you mess them up on the user mode level, and the debugging from the user mode is much easier. We also have built-in, or let's say in-house debugger. We have a debugging webinar as well. I recommend watching it. So again, the benefits are user mode, kernel developing and debugging, automated processes and generated code. We have DMA functions, interrupt handling functions, kernel plugin functions, and we're cross-platform. Two more things that I want to emphasize when talking about benefits. The first one is that we know that Windows and Linux are keep moving forward. They keep updating their kernels. Every kernel that comes out, not every, but a lot of time, newer kernel versions breaks things on our applications. We need to modify them. We on WinDriver are keeping updated with all the requirements from Microsoft and from Linux. And if you're utilizing WinDriver, you can be safe that we keep up with the requirements. And another thing I think that is a huge benefit when using WinDriver is our documentation. We have a very, very elaborate documentation, both in code and on a separate website. We have a lot of content on our website, and we have a support. Now, WinDriver exists for a long time, around 30 years, and still kicking. And we are also experienced. We saw many things. I'm talking about the development team, talking about the support. We have a very good support. We answer fast. We've seen a lot of things, and we try to help in whatever we can. So these are two other benefits of using WinDriver that you don't get when you develop drivers by yourself. We have two, as I mentioned, types of API, high level and low level. The high level APIs looks like this. Okay, they are being called from the user mode, and the low level APIs looks like this with the WD. Not just WD, but every function that starts with WDC is a high-level API of PCI functions. Every function that starts with WDU is a USB function, high-level USB function, and WDS is high-level server API. Every other name, like do, as we saw here, WD, these are low-level API functions. We recommend always working with high-level APIs. They are more advanced, they were developed in later times, and they are easier to work with. So be mindful, okay, because we will see both functions today. Now let's talk about the PCI Diag, our utility. So basically, the PCI Diagnostic app is a working sample application. It allows you to access your device. This is the first thing and first benefit of this utility. When you open it, and if you have your INF installed on your computer, you can gain access to your device, and you can read and write to it. You can allocate memory. You can raise interrupts, and without generating anything, without writing a single line of code, you can access your device and perform changes. We will do it in the demo part. The second benefit of the PCI Diag is that it is a working application, which means you can learn from it. You can see the code, you can see everything. You can see the headers, you can see the library, you can see the UI, the UI component, and see what we've done, how it looks like. How should you implement these functions on your driver? And in a lot of cases, we recommend from starting from the PCI Diag, maybe not even generating a code. You can start working with the PCI Diagnostic app and write to your device and see that you are getting the results you wished for. And it is also a great debugging tool. How so? Let's say you've generated your code, or you edited another PCI Diag utility, and things are stopped functioning. Okay, maybe it's the license, maybe it's another functionality. If you have the PCI Diagnostic app that was not untouched, you can use it as a debugging tool, because if it's working on the PCI Diag, that means that something is wrong with the code. Also, if it is not working on the PCI Diag, that means that something must be wrong with the device. Okay, since we're talking about a working diagnostic app, we checked and it works. So if things are not working, then something breaks along the way, either the device or the driver code. These sample, the PCI Diag samples come in C, .NET, Python, Java, and PowerShell on our sample folder. So this is an example of a C sample folder. You can see we have different samples. either USB diag, PCI diag, Lattice, Altera. And if you enter the PCI diag folder, you can see the components. Now let's talk about the PCI diag and PCI lib. On your generated app, you will see the same pattern. You will see the same components. The PCI diag means diagnostic. This is the UI. Okay, I will show a scheme soon in the next slide. And we have the lib, the library. This is where the brain sits. Okay, this is the let's say more UI functions, the interface, and this is the brain. This is the logic. Another component is the shared logic that all these samples share. So this is how it looks like. We have the UI, which is the PCI diag, .c. We have the logic, which is the PCI library, lib. And we have the shared logic that all the samples are using. And they are all linked and communicating with a high-level API. This is not related to the PCI Diagnostic app, but if you develop your own driver and you don't want to take the UI, you don't want to take the PCI diag file or components, you can generate a library, okay, a dynamic library, taking only the logic, both on Linux and Windows. On Windows, it's a DLL file, and on Linux, it's a .a file, okay? Then you can implement the logic on your user application. Now let's talk about the interrupt handler. We will see everything, where can you find the PCI diag and how to open the file in the live demo. Don't worry. Let's talk about interrupts. So an interrupt handler is a software routine that manages the response to the hardware interrupts. What does that mean? Let's go over the drawing. We have the hardware, okay? And the hardware, the device, some of them has an interrupt controller, okay? It's a physical component. It sits on the device. Once the hardware asserts a signal, the interrupt controller raises an interrupt, okay? And then comes our part, the driver part. The driver needs to listen to the device and listen to the interrupts. And once the interrupt is raised, it needs to be acknowledged, okay? The flow goes here. Once the interrupt is raised, it needs to be acknowledged by the driver and registered to the IRQ. Then there is an option for the user to send a callback or send a transfer command. We will talk about it in the next part. And it can loop, okay? The whole process can be looped until it is done. And then the interrupt is completed and disabled. So an interrupt handler manages this routine, okay? It listens to the device with the loop. It gets, once the interrupt is raised, it is getting the signal, it acknowledges the interrupt, and then it is doing what it is supposed to do. We will get to that part where we define the functions for the driver to send whatever it needs to send after the interrupt is raised. We will see a lot of code in this webinar. Most of the things we will see can be done via the wizard. Okay, I will not open the wizard in this webinar because I want to focus on the PCI Diagnostic app. But you can add access registers with WinDriver. If you will watch the introduction webinar, you will see that this is maybe the most common functionality WinDriver offers, to add access registers to your device based, of course, on your device specifications, and add transfer commands that will be sent to the CPU after the interrupt is raised. Okay, so you can add transfer commands from the wizard. We will see that in another section. And all of these, everything you will define here, of course, will be automatically generated as a working code on your project. Okay, so maybe the most important function for our case, for our webinar, is the WDC int enable. Okay, WDC int enable enables the interrupt on the device. It starts listening. It's not raising the interrupt, but it listens to the interrupt. This function receives an optional array of read and write transfer commands to be executed in the kernel when an interrupt occurs. So we have the int enable, WDC int enable, it initializes and start listening to interrupt. Okay, it runs in an infinite loop that's waiting for interrupt to occur. Once the interrupt is raised, as we said, a physical component in the device, it's getting acknowledged, then it can either get a transfer command or user provided callback. Then it sends whatever it needs to send, and if we don't want it to be disabled, the loop comes back to the raise, and if we completed, then the interrupt is disabled and completed. This screenshot is from our documentation. Okay, we will go over the components the function receives, and by that we will understand better what it does. Okay. So the first thing is the hdev. That simply it can handle to a WDC device returned by WDC PCI device open. We will talk about PCI device open. This function opens the device. Opens the device. Okay, it's a critical function. We will see in a short time how it helps us in the interrupt handling routine. It also gets a transfer command. This is optional. Okay, you don't have to send transfer command when executing the WDC int enable, but you can send transfer command to the executed to be executed after the interrupt is raised, and you can specify the number of commands that transfers in the ptrans commands. Okay, so these are the first three parameters that you need to define. Not need, these are optional, but can be defined in the WDC int enable function. Okay, so as I said, this is our flow, and now we will talk about what happens when you raise an interrupt, acknowledge it, and send a command, okay, a transfer command. Okay, sorry, this is the scheme of sending a transfer command. Okay, so you raise an interrupt, you acknowledge it, and send a transfer command. It can be in more than one sequence. And this is the case of sending a transfer command after acknowledging the interrupt. Now let's talk about types of interrupts, okay? Because this is critical for our next, for the next parameter. There are three types of interrupts: legacy, MSI, and MSIX. Legacy interrupts operate differently from MSI and MSIX. Legacy interrupts are older, okay? This is why they're called legacy. When a device requires attention, it asserts its corresponding IRQ line, okay? When it doesn't need an attention, it keeps the line low. However, if it does need an attention, it goes up, okay? And sends a signal, a continuous signal. Okay, the problem with continuous signal is that it's getting the CPU attention and can exhaust it. It drains resources, and it's not efficient and effective and not scalable. So if you can use other interrupts, not legacy MSI, we recommend doing so. Some devices support more than one type of interrupt. If you raise an interrupt and your computer hangs, okay, the first thing you should do is see what type of interrupt was used. Because if the driver utilizes the legacy interrupt, that might be it, okay? It hangs the computer. It won't crash it, but it will make the computer hang because it keeps the CPU occupied. And maybe the loop doesn't end, and you find the CPU find himself busy with this process. So be mindful of that. Technology advanced, and when we have the MSI interrupt, okay, that's when a device requires attention. It sends an interrupt message containing its assigned address and data to the CPU. Okay, so the difference with legacy is that it doesn't keep the CPU occupied. It sends a signal whenever it needs and raises the interrupt, sends the data, an address, and disable the interrupt. Okay, so it looks more like sharp spikes rather than like this. The MSIX is like MSI, but it's more scalable. It allows a single device to request multiple interrupts and assign different interrupt handler to each interrupt. But the most important thing to do is to make sure you're not using legacy if your device supports other types of interrupts, because the results can be unwanted. So going back to our function, the WDC int enable, on the DW options, it's a bit mask of interrupt handling flags. Okay, if you set the bit mask to 0 for no options or a combination of any of the following flags, okay, you have the legacy latch interrupt, level sensitive, MSI, and MSIX. Okay, so these are flags. A bit mask that represents flags in this parameter of WDC int enable. Okay, so you can get, you will see the interrupt type both on the PCI diag or your user app. And also you can track it with the WDC PCI get device info. This is before opening the device. Remember when we talked about it? The WDC PCI get device info returns information regarding the interrupt type supported by the hardware. Okay, it is stored in the DW options. Okay, so let's see how it looks like before opening the device. Yeah, how can we get the interrupt type before we open the device? We open the PCI diag, choose our device, and we can see that we have both a message signal interrupt, MSI, and level sensitive interrupt. This one has no interrupts. This one have both MSI and level sensitive. Okay, so you can get this information from both WDC PCI get device, and you will see the flag in the int enable, the bit mask of the flag on the int enable function. How does it look like on the IDE? Okay, you may recognize Visual Studio. So we've put a breakpoint on the WDC PCI get device info, ran the application, and we can see in the DW options that the value is 11. What does that mean? That's the bit mask. That means that 1 is level sensitive, legacy, and 10 is MSI. So we know that it supports the two types of interrupt, the level sensitive, the legacy, and the MSI. I hope that was clear. If you have questions, you can send me an email or go to our documentation and read more about these parameters and how to utilize them. Okay, so let's talk about this. Now it gets interesting. Func int handler is a user mode interrupt handler callback function. okay, which will be executed after an interrupt is received and processed in the kernel. Basically, this is the main parameter or function that is utilized during the WDC int enable, because here you tell the handler what to do or what to execute after the interrupt is raised, right? The function listens to interrupts, acknowledge it, and then you either send a transfer command, right? Or send a user-provided callback. So if you want to send a callback or perform other operations, you can modify the func handler function or program your own function, and of course, call it here. Modify the func handler to your function name. We will see now, the demo is very close. We will see how it looks like, okay? How can you modify this function or create your own? The pdata parameter, okay, is the data for the user mode interrupt handler callback routine. The data that will be added, or any function or parameter that will be applied here on the pdata, we will see it on pdev on our demo, will be utilized by the func handler. It has a great power, and I will show you now what I am talking about. And you can, this is a flag, okay? Either you use the kernel plugin or not, true or false. I will talk about kernel plugins and interrupt handler after the demo. So what I talked about just now is the other case, okay? When after the interrupt is raised and acknowledged, you write a function and provide a callback that is executed after the interrupt is raised. Let's see a live demo. Okay. I hope that you can see my screen. On WinDriver 16.3, I will enlarge the code, don't worry. Go to samples, see PCI Diagnostic. This is also available on the util folder, okay? We have the PCI Diagnostic app on the util folder, but we want to edit it. We want the source code. So we will go to the sample folder, see PCI Diag, and to the compiled user app. Let's open it. I don't know if you've utilized WinDriver before, but on the new version, we have colors on the command line, on the CLI, which is very, very nice, more pleasant to the eye. So let's find and open our device. Okay, I haven't installed anything but WinDriver, maybe the INF of the device. You can do it as well. Only just download WinDriver and scan your devices, okay? You can, if I press 1, it will scan a specific bus, but I want to scan all the devices on my computer. So I'm entering 2 zeros, and I can see a list of all the devices I have plugged to my computer. This is a virtual machine that has a virtual device, PCI device, but if you run it on your computer, you can see all the devices that are attached or connected to your computer. You can see the memory ranges of the bars. You can see the interrupts types. Okay, we have message signal, MSI, and level sensitive. You get general data on the devices, the bus, the domain, the slot, the function, and the VTPID. Our device is number 7. This is the device I want to open. Okay. And now I have, let's enlarge it even more. And I have different options. what to do with my device. Okay, you can see it here. I can allocate or free shared buffer. I can manage IPC, which is the multi-processes, read and write to the PCI configuration space, register or unregister plug and play and power management events, read or write memory and IO addresses, and enable, disable the device interrupts. Okay, can also allocate memory for DMA, which we are talking about in the DMA webinar. Now, I will raise an interrupt, but first, I need to start the int enable function. Okay, so before I am raising an interrupt, I will enable the device interrupt. Okay. I'm getting the warning that my hardware has a level sensitive interrupt. Okay. I will talk about how it chooses the interrupt type. It iterates between the different types of interrupts automatically, the int enable. But I'm getting a warning. It's not an error, it's a warning. Make sure that you raise the right interrupt so your computer won't be stuck. Okay, right now I have enabled the interrupt. Okay, I had the option 1, enable interrupt. I clicked it, the interrupt is enabled. And now there is an infinite loop that listens to interrupts from my device. Let's go back. And raise the interrupt. Now, how do you raise an interrupt on your device? That is device specific. You need to have an access register, okay, on your device that raises the interrupt. Each device has its own register. Go to your register page of your devices and see what makes the interrupt raise. Let's click 7, read and write memory. Okay. I want to write to an offset that raises the interrupt. In my device, the offset is 60 and the data is 1, for example. Let's see what happened. I got interrupt number 1. Okay, on offset 60. I wrote 1 to offset 60. In bar 0, I got interrupt number 1. Okay, this type is MSI, and I have the message data. Just like that, I haven't coded nothing. I haven't written a single line of code, and I was able to raise an interrupt. I haven't generated anything. It is just came with WinDriver. Let's raise another interrupt and see how it goes. Write to offset 60, give it the value 3. And we can see we got interrupt number 2. Again, MSI, row 3 to offset 60. Okay, that's that's really easy. We saw. Now I want to modify the PCI diag. Okay, I want to add a message. Let's disable the interrupt. Okay, and exit the diagnostic app. I've opened the PCI diag project. Okay, this is on Visual Studio using CMake. And now I want to add a message. I want to edit the program or the driver. So whenever an interrupt is raised, I will get a message. A message will be printed on my device. So let's see how easy it is to edit the code and make it work. Let's printf. This is my message after the interrupt was raised. Okay. Let's build it. Oh, sorry. Right, don't yell at me. Okay, build succeeded. Let's run PCI diagnostic app. Do it quick. Find my device. Choose number 7. Enable the interrupt. Write to the register that raises the interrupt. Okay. And we were supposed to see it. Maybe it hasn't been built. Let's try again. Okay. Okay, I'm going to have to troubleshoot it later. Meanwhile, let's see other things I wanted to show you in the demo. The first thing is the WDC int enable function. You can find it on the PCI lib.c. Okay, this is the function we talked about, the WDC int enable. We said that we have an handle for the handler. We have the transfer command. If you stand on the parameters, you can get more info, like here. We have the numbers of trans command. We have the DW option, which is the flag for the interrupt type, the bit mask for the flag, the PCI int handler, okay, which is what we talked about, the function, the pdev, and the kernel plugin. Now, let's see what PCI int handler is, and this is the function you can edit yourself. Let's go to this function, and this is the callback that we talked about, okay? This is the function that will be executed after the interrupt is raised. Now, you can modify it and edit here yourself, okay? Now, you can edit here yourself, or create another different, totally different function that will be executed after the interrupt is raised. This is where I had to add my message. Okay, I will run it later. But this is the function that will be run, the callback that will be executed after the interrupt is raised, and you can edit it and modify it yourself. And the pdata parameter, in this case it's pdev, we will see here, for example, that we have all the device information, okay? in this parameter. Now, all this data is being utilized or transferred by the function that we just saw. Okay, so you can enter whatever information you need to be utilized in the callback, in the function that is being called after the interrupt is raised, and add it here in the pdata, or in this case pdev. And it can be utilized again when the interrupt is raised. That's just for the sake of demo. Run it again. Very, very quick. Okay. This is the message presented after the interrupt is raised. So anything you want to add, any functionality you want to add to your program after the interrupt is raised can be done in this section, in the func handler, function handler, sorry, or any other function you are utilizing. Okay. Let's see if we need to present another. Raising an interrupt we've done, implementing a function on the interrupt handler done, the printf, and overviewing the function handler and pdata done. So we said that there are different, we have different interrupt types. So how a WinDriver knows which interrupt type it should work with? So WinDriver iterates between different types of interrupts. It first tries the MSIX, and then the MSI, and then the legacy. Okay, and if they are supported by the card, it stops iterating. If they fail, if it fails, both the MSIX and MSI, it works with the legacy. Okay, it enables the legacy level sensitive interrupt. So this is another thing we spare you from, the need to define which interrupt to use. It goes to the most advanced one and then starts downgrading. So we have macros that helps us to determine the interrupt type supported by the hardware. The WDC get int options macro returns the WDC device interrupt options bit mask. We talked about the bit mask. This way you can know how to access your which interrupt type you are currently using. The Windows API does not distinguish between MSI and MSIX. Therefore, on this operating system, the WinDriver function set the interrupt message flag for both MSI and MSIX. Okay, interrupt message, it goes without the X, it goes for MSI and MSIX. And another thing I want to add is that when you generate an INF, you need to specifically mention the interrupt in the INF generation page. If you don't want the legacy interrupt to be chosen or work on Windows, you can delete this section from the INF. This is a pro tip. And this way it will gain access only, your driver will gain access only to the MSI or MSIX interrupt. Okay, so we said that we have the sequence and we have the int enable and it listens to interrupt, and then an interrupt is raised and acknowledged, and then it can either send a user provided callback or a transfer command. Now, the user provided callback is what we saw with the function and the p data that it uses, and we have the transfer command. What is a transfer command? A transfer command is an optional array of read or write transfer commands to be executed in the kernel when an interrupt occurs. Okay, so you can define a transfer command, and when interrupt is raised, the transfer command will be executed. When using WinDriver to handle level-sensitive interrupts, the transfer command must be set for acknowledging the interrupt. Okay, so this is another thing. When we talk about legacy interrupts, the transfer command must be set for acknowledging the interrupt. It's not happening automatically. And another thing we need to remember is that memory allocated for the transfer commands must remain available until the interrupts are disabled. Otherwise, you will get an overlap. On our website, I know this is a lot of text. We won't go over everything here. I just want to say this is an example of a transfer command. It is available on our documentation. You can read just, this is the text on chapter 10.1.6.2. This is an example of implementing a transfer command. You get a good sense of what it is, the arrays, the functions, the functionality, what it needs in order to create the sequence. And this is the hard way to do it. The more easy way is on the wizard, okay? On WinDriver's wizard, the driver wizard, you can create access registers. You can add transfer commands, okay, to the interrupt. In this case, I thought of a PCI device that gets an image and it processes it, and it needs to raise an interrupt once it gets it, moving it, and transferring it, for example. So I created a remove image, transfer image, and get image transfer commands, and the data is being written, okay, to the access register. This is the transfer command, and it will execute once the interrupt is raised. So I've generated the code, my code, and I can see that it was generated automatically, the transfer command. Okay, we can see here the list. Right to the remove image register, I have the address, I have the offset, okay, offset 64, and I have the data that is being written, and you can create the transfer commands on the GUI wizard. It will be much more convenient than writing it yourself, and then just copy and paste it to your existing code. Or you can work with the generated code as well. So these are transfer commands. Okay, just to wrap it up, the other branch. After defining the transfer command, you can proceed to enable the interrupt. Memory allocated for the transfer command must remain available until the interrupt is disabled, as explained before. The following code demonstrates how the WDC int enable function to enable the interrupt using the transfer commands prepared above. Okay, so here we have an example. We have the hdev, we have the trans, packets of 3. We have the flag, as we talked about, the interrupt handler and pdata, the callback that it is using, and we are not using a kernel plugin. Okay, so this is an example. You can see it again on our documentation. It is written in both text and code snippets. The last thing we will talk about, no, we have also the kernel plugin, but one before the last thing is an IPC. We will have a full dedicated webinar to IPC on September, as I said. I will not discuss it thoroughly. If you don't understand something here, go to our documentation and sign up for the webinar because this is a very interesting feature. So IPC is an inter-process communication. It allows several WinDriver-based user applications to send and receive user-defined messages. So we know that the device is very sensitive. It can't be messed around with too much. If one process is overwriting the other process, the kernel will break, and things can get very messy. So what we offer, the solution, so let's say in this case, if you have two processes that needs to access your device, This one needs, you need to have a mechanism that create access control. Okay, so both of them won't create a resource overlap. You need to make sure that there is no memory corruption, that one is writing on the other's process's memory. And it can be quite a headache. What we offer is a different thing. We offer a special API. Okay, it costs. It is being sold separately from WinDriver's license. So one process can listen to the other process. Not listen. One process can communicate with the other process, process one with process two, and process two is communicating directly with the device. This way, you don't need to have all this mechanism and chaos or optional chaos using the IPC. It is also exemplified on the PCI Diag utility. Okay, so if you open the PCI Diag, we saw there. Okay, one of the options is inter-process communication. I set the IPC. We will deep dive into it in the webinar, as I said, on September. Why am I talking about it right now? Because we have a shared interrupt feature, okay, with this API. You can register the processes to IPC using WDS, remember, server, IPC register. You can write your own callback function that is relevant to what you wish to occur when a shared interrupt occurs. Send a pointer to that function as an argument to WDS shared int enable, and write different callback for each process to achieve a different heading of the interrupt in different contexts. So instead of processes that are connected to a device and they need to listen and the interrupt doesn't know which process needs which message, etc., you can have everything managed with one process that listens to the interrupt. Interrupt is sent to process one, and it sends the relevant information to process two and process three. You can also disable the shared interrupt using the WDS shared int disable local for subgroups or global, okay, for all the groups. Sign up for the launch an IPC webinar. It will be interesting. The last thing we will talk about is the kernel plugin. Kernel plugin, if you're not familiar with the concept, is chunks of code that sits in the kernel. Since we have a high-level API that operates from the user mode to the kernel mode, we have a context switch. It can be not too efficient, okay, in terms of performance. So if you want to improve your device performance, you can create a kernel plugin, regardless of interrupts. You can create a kernel plugin even without interrupts, but you can create an interrupt handler inside the kernel plugin, which assures an immediate interrupt trace because everything takes place on the kernel mode immediately. So there is no context switch. Your driver will work faster, respond faster, and your interrupts will be raised immediately. So this is another feature we have, and on the int enable WDC int enable function, raise the flag of the kernel plugin to true. In this way, the interrupts will be raised with the kernel plugin. You can also send transfer commands from the kernel mode interrupt, okay, using the WDC int enable, and receive transfer command information. If a kernel plugin driver is used to handle the interrupt, any transfer command set by the caller will be executed by WinDriver after the kernel plugin kp int dpc or same one with MSI function completes its execution. Okay, and there is another thing you need to be aware of when you're using legacy interrupts. You must prepare and pass to the function transfer command for acknowledging the interrupt. Okay, again, legacy interrupts needs a special transfer commands to acknowledge the interrupt. It doesn't happen automatically like MSI and MSIX. And that's it for the kernel plugin interrupt handling. I want to thank you for listening and joining and staying here by now. This is my contact information, okay? danielb@django.com or our sales team. You can reach out whenever you want and ask questions regarding anything I just talked about and more. Thank you and have a great rest of your day.